This LOS is identify the appropriate test statistic and interpret the results for a hypothesis test concerning 1. The variance of a normally distributed population, and 2. The equality of the variances of two normally distributed populations based on two independent random samples. Test concerning a single variance. In this test about the value of the variance of a single population, we use variance not to denote the hypothesized value of the variance. So we can formulate three hypotheses again as follows. The first one, the null hypothesis that the variance equals the population variance, versus the alternative hypothesis that it does not equal. So that's a not equal hypothesis. That'll be the two-sided. Number 2, we can look at the null hypothesis that the variance is less than or equal the population variance. So versus the alternative hypothesis that it's greater than. So that's a greater than hypothesis. And finally, we have the less than hypothesis. So in tests concerning variance, we're using as the test statistic the chi-squared. It's no longer the t-stat, we're using the chi-squared. So that's a different table in the appendix at the back of the book, okay? And in the numerator, we have n-1 times the variance divided by the population variance. So that's the variance of the sample divided by the population variance. So n-1 times the variance of the sample divided by the population variance. With n-1 degrees of freedom in the numerator of the expression, again, that's the sample variance, okay? So we're going to work through an example again and then a practice problem for this LOS. Okay, before we work through the example, this is a very important slide because it's talking about the rejection points for the hypothesis tests on the population variance, okay? So you can see, I'll start at the bottom and then work my way back up. You can see that in a less than hypothesis, you reject the null hypothesis if this test statistic is less than the lower point of the chi-squared distribution. So remember when we were doing our t-stats, and if the number was greater than our critical value, we would reject. And if it was less than, we would accept or fail to reject. But in this case, it's the opposite. We reject the null hypothesis if the test statistic is less than the lower point. That's for a less than hypothesis, okay? For a greater than hypothesis, we reject the null if the test statistic is greater than the upper point. And for a not equal, we reject the null hypothesis if the test statistic is greater than or less than the critical value of the chi-squared, okay? So that's a little bit different. You have to be careful with which type of hypothesis that you're doing, and then when you calculate your test statistic and you're comparing it versus the critical value, if it's a less than hypothesis, we reject the null if the test statistic is less than the lower point, and if it's a greater than, we're going to reject the null if the test statistic is greater than the upper point of the chi-squared distribution. So now we'll work our way through an example of a test concerning a single variance, which is in the text. So it's Sendar Equity Fund, a mid-cap growth fund that has been in existence for only 24 months. So we have our N equals 24. Recall that during this period, Sendar Equity achieved a sample standard deviation of monthly returns of 3.6%. You now want to test a claim that the particular investment disciplines followed by Sendar result in a standard deviation of monthly returns that is less than 4%. So it's a less than hypothesis. So what are we going to do? Number 1, we're going to formulate the null and alternative hypothesis consistent with the verbal description of the research goal. We're going to identify the test statistic for conducting a test of the hypothesis in part 1. We're going to identify the rejection point or points for the hypothesis at the 5% level of significance. And then finally, we're going to determine whether the null hypothesis is rejected or not rejected at the 5% level of significance. We're going to use the tables at the back of the text. So we'll start with the first part, which is to formulate the null and alternative hypothesis consistent with the verbal description of the research goal. So as I had mentioned, we have a less than alternative hypothesis, where the standard deviation is the underlying standard deviation of return on Cendar equity fund. So you need to be careful because these are tests concerning a single variance. So what do we need to do? It said that the Cendar resulted in a standard deviation of monthly returns less than 4%. So the hypothesis is that the null hypothesis is that the variance is greater than 16, which is 4 squared, versus the alternative hypothesis that the variance is less than 16. So for the second part, we're going to identify the test statistic for conducting a test of the hypothesis. So we're going to use the chi-squared tables at the back of the text in the appendix, and the critical value is going to be, we're going to look at 24 minus 1 equals 23 degrees of freedom, because the fund has been in existence for 24 months, so n equals 24 degrees of freedom, n minus 1 equals 23. And then, recall that for the less than hypothesis, we reject the null hypothesis if the test statistic is less than the lower point of the chi-squared distribution with degrees of freedom of n minus 1. Okay, so I've cut out from the back of the text the some data from the chi-squared tables, okay? So you can see on the rows we have the degrees of freedom. So we calculated it was 24 months, so n minus 1 equals 23. So that we went to the row 23, okay? The second thing we said we were going to test for at the 5% level of significance, and we knew that it was one-tailed because we were looking at a less than hypothesis. So we would go along row 23 and column 0.95, and then we have the critical value for the chi-squared, which is 13.091. And again, we're going to reject the null if the test statistic is less than 13.091. So now we're going to determine whether the null hypothesis is rejected or not rejected at the 5% level of significance. So as I just showed on the previous slide, the lower 0.05 rejection point is found for the line of degrees of freedom equals 23 under the 0.95 column. And so the rejection point is 13.091. We will reject the null if we find that the chi-squared is less than 13.091. So finally, what we need to do is we need to calculate the test statistic, and it's n minus 1 times the variance of the sample divided by the variance, the hypothesized variance. So n minus 1 equals 23, and I put into bold green the sample standard deviation of monthly returns is 3.6%, so we need to square it. So it's 23 times 3.6 squared divided by 4 squared. Okay, so that gave us a chi-squared calculation of 298.08 divided by 16, and so we calculated 18.63. So because 18.63, the calculated value of the test statistic is not less than 13.091, we do not reject the null hypothesis. We cannot conclude that Cendar's investment disciplines result in a standard deviation of monthly returns of less than 4%. Suppose we have a hypothesis about the relative values of the variances of two normally distributed populations with means of mu1 and mu2 and variances of variance 1 and variance 2. We can formulate all hypotheses as one of the choices below. So we have the null hypothesis that the variants are equal versus the alternative that they're not. The null hypothesis that the variance of 1 is less than the variance, or less than or equal variance of 2, versus the hypothesis that it's greater than. And finally, the null hypothesis that the variance of 1 is greater or equal to the variance of 2 versus the alternative hypothesis that the variance of 1 is less than, which is a less than. So for this test, when we calculate the test statistic, it's the variance of 1 divided by the variance of 2, and we come up with an F test. And so again, we're going to use a different table in the back of the book. It's the F distribution, and it's a family of asymmetrical distributions bounded from below by 0. Okay? Each F distribution is defined by two values of degrees of freedom called the numerator and denominator degrees of freedom. So you can see the numerator degrees of freedom, n1 minus 1, and the denominator is n2 minus 1. So we're going to finish this LOS with a practice problem. And you can see with this practice problem, they're giving you a lot of data. So speed is a skill. Skill gets rewarded on the CFA exam. You've got 90 seconds per question. So sometimes the challenge is to read the question, look through the data, and pick out the data that you need very quickly. So this looks like a lot to start with, but you see you'll see when we work through our way through the question that that's actually not all that difficult. So let's jump into it. So it says, using the data beside, an analyst is trying to test the null hypothesis that the population variances are equal against the alternative hypothesis that the variances are not equal at the 5% level of significance. The table of the F distribution is provided below. So they've given you the F distribution. But the issue is that they've given you panel A, critical values for right-hand tail areas equal to 5%, and panel B is critical values for right-hand tail areas equal to 0.025. Okay, so you can see that you're being asked to test at the 5%, but they're giving you the two tables. Which table do you need to use? Well, you have to realize, is it a one-tailed test or a two-tailed test? Okay. So again, looking at the top, we have two populations, population 1 and population 2. The sample size of 1 is n equals 5, and the sample size for 2 is also n equals 5. We have our sample variance for 1, it equals 4, and our sample variance for 2 equals 28. It says the samples are drawn independently and are both populations are assumed to be normally distributed. So what the question is which of the following statements is most appropriate? The critical value is A, 6.39 and reject the null, B, 7.15 and do not reject the null, or C, 9.6 and do not reject the null. So actually all they want you to do in this question is determine what the critical value is for the test. They're not even asking you to calculate the test statistic in this case. Okay, the key to success in this question is, number one, is to understand the hypothesis and the alternative hypothesis. So you can see the alternative hypothesis is that the variances are not equal. And when it's a not equal alternative hypothesis, then it has to be two-sided, okay, two-tailed. And when you're looking at the 5% on a two-tailed, then you're always going to be looking at the column, the right-hand tail areas for the 0.025 because it's two-tailed. So 0.025 on the left tail plus 0.025 on the right tail is going to equal your 5%. So a two-tailed test, you need to use the panel B, okay? The second thing is that we saw that the sample size was 5 and 5, so you need to know your degrees of freedom, which is always n minus 1. So we're looking for the row 4 and the column 4. So you can see that A was giving us the 6.39, but no, that's wrong because you would be using the 5% panel A, and we know that we needed to use the 0.025. So B we didn't even have to do because if you've got your rows and your column right, you know that the correct answer has to be C, that the critical value is 9.6 because you're doing a not equals alternative hypothesis and the degrees of freedom were 4 and 4 and it's a two-sided test, so you had to be using the 0.025. So the correct answer was C, the critical value is 9.6 and you do not reject the null. That's the last slide for this LOS. Thank you very much.